You ever see a graph that just shoots off to infinity, but instead of flattening out, it looks like it's following some invisible diagonal line? What's going on there? Well, today, we're explaining the answer to that, slant asymptotes. These are the tilted guidelines that tell us exactly where a graph is heading. So let's get right into it.
Here's our game plan. First, we'll unravel the mystery of these tilted lines. Then we'll cover the one super simple rule you gotta know. After that, we'll jump into the how, the exact division method to find them. Of course, we'll do some practice problems. I'll show you the common mistakes to avoid, and we'll wrap up by seeing where this stuff actually shows up in the real world.
All right, let's kick things off with Section 1, the tilted asymptote mystery. We're all pretty used to seeing graphs with horizontal asymptotes, right? Where the function just kind of chills out and levels off at some y value. But what happens when it just keeps going up and up, or down and down forever?
I mean, think about it. If a graph doesn't settle down horizontally, it has to be going somewhere. And for some special functions, that somewhere isn't just random chaos. The graph actually starts to cozy up to a perfectly straight diagonal line. It gets closer and closer and closer the farther out you go. And that invisible guideline, that's our slant asymptote.
So how can you tell if a graph even has one of these cool tilted asymptotes? Well, it turns out there's one beautifully simple rule. It's the first thing you should check every single time.
And here it is, the golden rule. A slant asymptote exists if and only if the degree of the polynomial on top is exactly 1 bigger than the degree on the bottom. Not 2 bigger, not the same, exactly 1. So if you see an x squared over an x, or maybe an x cubed over an x squared, bingo, you've got one.
Okay, now for the fun part. You've checked the degrees, you've confirmed a slant asymptote exists, so how do you actually find its equation? Well, the key is something you've probably done before, polynomial division. Let's break down how it works.
So any rational function can be broken down like this. When you divide the top by the bottom, you get a quotient, and that's going to be your line, something like mx plus b. And then you have some leftover bit, the remainder, that's still being divided by the original denominator.
Now here is the big aha moment. What happens when x gets ridiculously huge? I mean, we're talking way out towards positive or negative infinity. That little leftover fraction, the remainder over the divisor, has a massive number in its denominator. And what happens when you divide by a huge number? The whole thing just shrinks and shrinks until it's practically zero. It becomes totally insignificant.
So what's the big takeaway from that? For finding the asymptote, that leftover piece, it effectively vanishes. It's a goner. We're going to completely and totally ignore the remainder.
And that leads us to the beautiful, simple conclusion. Since that remainder part disappears as x gets huge, our function starts to behave exactly like the quotient part. That means the equation of our slant asymptote is just y equals the quotient. It's that clean.
All right, enough theory. Let's get our hands dirty and actually do some problems. We're going to run through a few examples to make sure this is all crystal clear.
Okay, example 1. First things first, check the degrees. We've got degree 2 on top, degree 1 on the bottom. The difference is 1, so we are good to go. Since the divisor, x plus 1, is a nice, simple linear term, we can use synthetic division. We pop our coefficients 1, 4, and -5 into the setup. We run through the process, and that bottom row gives us everything we need. The 1 and 3 become our quotient, 1x plus 3. That -8 is the remainder, and what do we do with the remainder? We ignore it. So the asymptote is y equals x plus 3. Done.
Now for a different beast. Degrees are 3 and 2, so the difference is still 1. Perfect. But look at that denominator, x squared minus 1. That is not linear, so synthetic division is off the table. We have to use long division. But wait, here's a fantastic little trick. You only need the quotient. You don't care about the remainder. So you can just ask, what's 2x cubed divided by x squared? It's 2x. And what's -4x squared divided by x squared? It's -4. And we can stop right there. That's our line. The slant asymptote is y equals 2x minus 4. And let's do one more quick check because this is so important. Look at this function here. The degree on top is 4, and on the bottom, it's 2. What's the difference? It's 2. And because that is not exactly 1, this function does not have a slant asymptote. It does something else as it goes to infinity, but it's not a straight line. Always, always, always check the degrees first.
Okay, let's talk about the 2 most common mistakes people make with these problems. Think of this as your pre-flight check to make sure you don't crash and burn on a test. This is by far the biggest trap. People will do all the division correctly and then include the remainder in their final answer. No, remember, the whole reason this works is because that remainder piece goes to 0. The asymptote is a line, it's what's left after the remainder disappears. Your answer should always be a clean, simple y equals mx plus b.
And the second pitfall is using the wrong tool for the job. Look, synthetic division is awesome. It's fast, it's clean, but it only works for simple linear divisors, something like x minus a number. If your denominator has an x squared, or even just a number in front of the x, like 2x minus 1, play it safe. Just use long division. It'll save you from making a silly mistake.
So, you might be sitting there thinking, okay, this is a neat math trick, but when would I ever actually use this? Well, let's check out a really cool real-world application from economics.
So in business, you've got a total cost to make something. It includes fixed costs, like rent for the factory, and variable costs that go up with each item you make. If you want to find the average cost for just one item, you just take that total cost function and divide by x, the number of items.
And would you look at that? The average cost function is a rational function. When you do the division, you see that the fixed cost, that $5,000, is now over x. So what happens as you scale up production and x gets massive? That fixed cost gets spread so thin that the 5,000 over x part just melts away to nothing. And what are you left with? A slant asymptote. That line, y equals 0.1x plus 10, tells the company the true long-run cost per item once those initial setup costs don't really matter anymore. Pretty cool, right?
So there you have it. The slant asymptote is that secret guideline telling you where a graph is headed. You know the 1 degree higher rule, you know how to use division to find the equation, and you've even seen how it shows up in economics. You have officially mastered the guideline. So the only question left is, are you ready to sketch the rest of the curve?